Today, myself and Isabella are going to be talking about soft body simulation in Isaac Gym, and we're doing it slightly differently. We actually have pre-recorded presentations. Hopefully that'll also make it easier to post on YouTube afterwards or post links in our repos. But we're both here and we'll be able to answer questions in the chat and also afterwards live. And the last thing I just want to mention as the intro is that if you have stuck around thus far and you're in soft body simulation now, you might be interested in a workshop that we're hosting on Thursday, also at RSS on deformable object simulation in robotics. So take a look at that. All right, I will now share my screen and play the video.
Hi, I'm Yashraj Nara. Isabella Huang and I will be talking about how to use Isaac Gym for soft body simulation. We'll also present 2 case studies that might be of particular interest for robotics, simulating soft tactile sensors and simulating robotic grasping of soft objects. First of all, what do we mean by soft bodies? There are many different types of deformable materials and structures, such as rope, cloth, 3D deformable objects, liquids, and granular media. Among these, Isaac Gym is currently best suited towards simulating 3D deformable objects, which will be the focus of this talk. This category of objects includes soft tactile sensors, fruits and vegetables, thick-walled bottles and containers, and internal organs. Note that Isaac Gym can also be used to effectively simulate granular media. For an example, please see the following paper. Upcoming versions of NVIDIA simulators will also be able to effectively simulate the remaining categories of deformable objects. For more information, please watch the New Frontiers talk later today. There are many ways to simulate soft bodies. For example, there are mass spring models, the finite element method, or FEM, and position-based dynamics, or PBD. In particular, FEM is well established as one of the most principled and physically accurate ways to simulate the deformation of solids. It divides complex 3D objects into small volumetric elements, which in graphics are typically tetrahedra. It then formulates equations of motion and deformation for each element and solves the system of equations. For a concise, technical overview of FEM theory, please see the finite element theory section of the following paper. Isaac Gym implements a version of FEM known as co-rotational FEM, which decomposes the motion of each element into a potentially large rigid body component and a small deformational component. Now let's look at the soft body example that comes with Isaac Gym. I've navigated here to the Python examples folder. I'll now run softbody.py with the flex flag, which is required for simulations with soft bodies. We see 4 deformable spheres with different material properties, bouncing and sagging under gravity. The colors here represent von Mises stress, which is a scalar form of stress that is particularly useful for determining when a material might yield and permanently deform. We also see a suspended platform above each of the spheres. If we'd like, we can go to the DOFs panel and interactively modify the position targets for the built-in proportional derivative position controller for the platforms. Let's look at the corresponding Python script to see how to create. There are a few features of a soft body scene that might be slightly different from the scenes you have seen earlier in this workshop, as well as the other Python examples in Isaac Gym. First, as we previously mentioned, the physics engine must be set to Flex. Isaac Gym provides 2 physics engines called Flex and PhysX, and currently only Flex supports soft body simulation. Second, the recommended solver type is 5. This corresponds to a GPU-based preconditioned conjugate residual solver, or PCR, which provides efficient and stable performance for stiff deformable meshes. For a detailed description of the solver, as well as other numerical methods used in Isaac Gym, please see the following paper. Third, there is a thickness parameter for soft assets, which adds an artificial thickness to the soft body to mitigate interpenetration. The value of this thickness should be tuned based on the expected velocities in your simulation, the time step size, and of course, testing. Finally, there are methods for getting and setting the material properties of the soft bodies. These are initially set by a URDF asset description file, but can be modified in the Python script. Now let's take a closer look at the URDF file for this softbody example. The most important thing to note is that the softbody is defined as a link with an FEM tag. Here, you can define the density, Young's modulus, and Poisson's ratio, as well as a non-zero damping value if you'd like. You can also define an attach distance. If any vertices of the soft body are less than or equal to this distance from a rigid body at the start of the simulation, those vertices will become attached to the rigid body. This is obviously not used in this simulation, but it's useful for other ones, such as the biotech example that we will show next. Finally, there is a tetmesh tag, which references a tet file. This is a very simple file that lists the coordinates of the vertices of the tetrahedral mesh, as well as the indices of the vertices comprising each tetrahedron. If you have an arbitrary surface mesh, for example, an OBJ file, you can easily generate a tet file. We'll be discussing a typical procedure later in this talk. As a first example of using Isaac Jim's soft body simulation for robotics, I'll show a quick demo of sample simulation code released as part of the following ICRA paper. This paper focuses on efficient simulation of the biotech tactile sensor, as well as learning-based prediction of sensor output. The sample code can be found at the following URL. On execution of this code, you can see 8 biotech sensors distributed across 8 parallel environments. In each environment, the biotech is contacted by a uniquely shaped indenter. The biotech itself consists of rigid parts attached to deformable parts. After the objects indent the biotech by a few millimeters, the simulation completes, and the results are exported to an HDF5 file. If we open the HDF using, for example, HDF View on Windows, we'll see that there is a separate folder for each time step. If we open a particular time step, we'll see separate folders for the 2 quantities that were exported from the simulation, net force vectors, and the coordinates of the nodes of the biotech mesh. Finally, within each of these folders, we can find the corresponding data for the 8 biotechs. Now, if we open the script, we'll see at the very top a concept that defines the target pose of the objects contacting the biotech, as well as the command line arguments and their default values. In the extract results method, we'll see that separate methods are called to extract net forces, nodal coordinates, and optionally, the stresses within each element of the biotech mesh. There are also useful methods to reset the states of the deformable biotech and rigid indenters to arbitrary desired states. Finally, if we open the URDF file for the biotech asset, we'll see an example of attaching a rigid body to a deformable body using a non-zero attach distance. Let's discuss one more point. A common question is, how accurate are the soft body simulations within Isaac Jim? The answer to this question depends on many factors, such as the type of solver, the size of the time step, the number of iterations, and the refinement of the meshes. It is always worth setting these parameters conservatively and checking the results against a commercial FEM code, real-world data, or both. For an example of such a procedure, see the FEM validation section of the previously mentioned paper. We showed that our Isaac Jim model closely matched results from a commercial simulator, which itself was validated against the real world. We'll now discuss a second, more in-depth example of how to use Isaac Jim's soft body simulation for robotics.
I see them. I was just going to read through them. So I'm wondering what happens if we try to stretch the soft bodies. Will a simulator be able to simulate tearing if we stretch too much? Right now, the simulator cannot simulate tearing. We've actually kind of explored this problem through a proxy. I think Isabella will talk a little bit about that work, where we basically identified locations that an object would tear by basically trying to see where the local stress greatly exceeded the damage or the yield threshold of that object. And we were able to validate that in real life. But the simulator itself cannot simulate tearing at this point. Next question is, what does a damping value represent? So this is a material damping parameter. So it is like as if you wanted to model, let's say, viscoelastic behavior of your object. So it's, yeah, it's essentially a viscous parameter. Thank you for the presentation. Is it possible to add textures or somehow colorize the soft bodies except the stress level? I did not find this feature in the examples or in the docs. As I understood, TET file does not support it, neither URDF with the FEM tag. So I'm not aware of any way to do this right now in Isaac Gym. Right now, the default texturization for the FEM objects is the von Mises stress. That being said, I'm sure this is a feature that you might be able to request. If it's not an Isaac Gym, I guess it could be something for Omniverse. Is that correct?
Yeah. So I think most of the future soft body work will be done in the next iteration, so in OmniGym. So we'll speak more to that a little bit later on, so I don't want to get ahead of myself. But at the same time, if this is a feature that's easy for us to add, there's no problem asking for it. So we still continue to maintain and support Isaac Gym as its own product, and we intend to continue that for the next little while anyway. So it's perfectly fine to request that feature. Hit us up on the forums, on the dev forums, and you can request the feature there.
Sounds good. Okay, I'll hand it over to Isabella then.
Okay, cool. Hi everyone, my name is Isabella Huang. I'm a grad student at UC Berkeley, and I'm also an NVIDIA intern who works with Yash. So I'll be introducing DefGrasp Sim, which is our code base that we've written to automatically evaluate grasps on a deformable object. This code base accompanies a paper that we'll be presenting at the DOSIM workshop later this week. And the paper should also be up on arXiv by the end of this week. So please check that out too. So I'm gonna share my video. It's also a pre-recorded video. So,
hi everyone, my name is Isabella. I'll be taking over for the next part of this presentation. I'll be talking about evaluating grasps on deformable objects with DefGrasp Sim. So DefGrasp Sim is the accompanying codebase and dataset for our paper that will be presented at the DOSIM workshop. It's a pipeline that automatically evaluates grasps on deformable objects using Isaac Gym. And today I'll be explaining how researchers can work with this code. So here's an outline of what we'll be going over. First, we'll see an overview of the grasp pipeline that DefGrasp Sim implements. Then we'll talk about what exactly we evaluate for any given grasp. We'll also talk about other values that are measured prior to the full evaluation of the grasp, and these are called grasp features. Then we'll look at an example of running this code, and finally we'll show some results from validating simulated experiments in the real world. Let's start with going into an overview of the grasp pipeline that's implemented by DefGrasp Sim. Now, this pipeline is applied to one object and one grasp pose. In this example, we have a cup as the object and a grasp pose that's represented by its line drawing in green. Our script then takes this object and grasp pose and initializes them both in the Isaac Gym environment. Note that the object is initialized to be resting on a platform and the gripper is initialized with its fingers open. Then the gripper closes and squeezes the object until the desired squeezing force Fp is applied. This squeezing force is calculated automatically. For example, prior to performing a pickup evaluation, which is one of the 4 grasp evaluations that we'll go over next, this Fp is the normal force that applies enough frictional force to overcome gravity. Once Fp is applied, the load phase begins. In this phase, the platform is slowly lowered while the gripper stays in place, which induces incremental gravitational loading. Then, one of 4 grasp evaluations is performed according to the user selection. These evaluations include pickup, linear acceleration, angular acceleration, and reorientation. We'll now go over what each of these does. The first type of grasp evaluation is pickup. For pickup, the gripper applies Fp. Then the object is loaded until its weight is completely supported by the gripper. Once the object is successfully picked up, the stress and deformation distributions over the entire object are recorded. Otherwise, if the pickup fails, a failure is recorded. The second type of grasp evaluation is linear acceleration. For linear acceleration, we first go through the same pickup process, and once pickup is achieved, the gripper accelerates along an axis under a constant jerk. The script then records the instability along that axis, which is defined as the acceleration at which the gripper loses contact with the object. In total, there are 16 different axes of acceleration for which instability is measured. The third type of grasp evaluation is angular acceleration. It's almost the same as the previous linear acceleration case, except that the gripper this time accelerates about the 16 axes rather than along them. Again, instability is recorded as the angular acceleration at which contact is lost with the object. The fourth and final type of grasp evaluation is reorientation. During reorientation, the gripper slowly rotates the object about each of the 16 axes, thus reorienting the object. The purpose in doing this is to measure how much additional deformation post-pickup can be achieved just by reorienting the object. We call this additional deformation through orientation as the deformation controllability. Deformation controllability will depend on the envelope of shape changes that are induced during reorientation. Now that we've gone through each of the 4 grasp evaluations, you'll notice how we measure different quantities at the end of each. These quantities are what we call performance metrics, and these are what practitioners care about after applying a certain grasp. For example, we measured the stress of the object after pickup, because practitioners may care about seeing whether a grasp will induce stresses that are past the breaking point of the material, and if so, they should probably want to avoid using that grasp in the real world. We also measure deformation as a performance metric, because this may be important for someone handling containers, for example. For instance, if one is trying to squeeze the ketchup out of a bottle, they'd want to choose a grasp that applies the most deformation. But on the other hand, if someone's trying to pick up a box of crackers, they'd want to check which grasp applies the least deformation, and therefore the least damage to the crackers inside. For the full list of performance metrics that we measure, as well as their motivations, please refer to our paper. Of course, we encourage researchers to tweak this code to record whatever performance metrics that they care about most for their own purposes. I also want to mention that our code also measures quantities that we call grasp features. These are quantities that are measured right after the squeeze phase finishes, that is, right before loading begins. The purpose of measuring these grasp features is that they may be predictive of the performance metrics that are measured later on. Thus, researchers can try to predict performance metrics without having to run the full grasp evaluations. In our code, we explicitly measure the following 7 grasp features. These include quantities like the contact distance from the centroid, the number of contacts, the squeezing distance of the grippers, etc. While we record these 7 features, we actually do know the entire state of the object in simulation. This includes the entire object's nodal positions, its stresses, which of its nodes are in contact with the gripper and platform, as well as full proprioceptive information of the grippers. This high-dimensional state information is made available so that researchers can design their own custom features beyond the 7 that we record. I'll now show you guys how to use this codebase with any object of your choice. The first thing to do is to clone the GitHub repo and to follow the installation instructions. So I've downloaded this model of a foam brick from the YCB dataset, and I'm now visualizing it in MeshLab. We can first do some pre-processing to simplify the mesh, which helps our simulation run faster later. You can use a simplifying filter in MeshLab. Here I'm using the quadric edge collapse decimation filter several times. And once I'm done, we go from having around 5,700 vertices to less than 700 without compromising detail. Next, generate your grasps of interest however you'd like. Here I'm using an external antipodal sampler to generate 50 random grasps on the foam brick, as visualized by line drawings here. To hold all the information about this new object, I've created a new folder under Examples called Foam Brick. Inside this folder, I have the original scan from the YCB dataset, the simplified version of the scan that I created using MeshLab, as well as an H5 file that represents the grasps that I generated. However, the object is currently saved as an STL file, but we need the object to be represented as a tetrahedral mesh. I recommend using ftetwhile to perform this tet meshing. It's pretty simple to use. All you have to do is specify the input file, foambricksimplified.stl, and the output file, foambrick.mesh. Once it finishes running, you'll see the desired output file, as well as some intermediate files that I usually just delete. But we're not quite done yet because IsaacGym reads meshes in the tet file format, not the mesh file format. To make this conversion, there's a script called mesh-to-tet.py in the repo. Edit the input and output file paths, run the script, and there should be a new tet file in the output file path. We need to include one more file in this foambrick folder called softbody.urdf. Let's copy the one from the rectangle object folder that's included by default in the repo. Softbody.urdf contains all the values for the material properties of the soft object. However, the only important thing we need to change now is the name of the tet file path. So let's change that from rectangle.tet to foambrick.tet, which is the tet file that we want the simulator to load. We run grasp evaluation, set the object name to foambrick. We're going to set the Young's modulus, density, and Poisson's ratios to reasonable values for foam. Then we can specify the index of the grasp candidate that we want to evaluate. Since we generated 50 grasps in total, this index goes from 0 to 49. Let's just choose 0. We set the mode argument to the name of the grasp evaluation. Let's do pickup. Finally, we add the write flag so that all of the performance metrics and grasp features are saved to a file. The simulation will start to run with the foam brick initialized in the environment and the robot hand initialized in the grasp pose. The fingers will close and squeeze the object. And then the platform will lower until the object is picked up by the gripper. Once picked up, the simulation ends and an H5 file of results will be generated. Let's try another evaluation this time, and let's change the mode from pickup to linear acceleration. Recall that for linear acceleration, there are 16 different vectors of perturbation that we can evaluate. These can be simulated at the same time, where ORI start and ORI end flags sets the range of these vector indices. ORI start can be at minimum 0 and ORI end at maximum 15. For the sake of speedier simulation, I'm going to set ORI end to 1. This time, 2 environments will be generated, one for each vector of perturbation. The grippers will squeeze the objects and the platforms will lower. Then the grippers will increasingly accelerate in the directions of the vectors of perturbation. The simulation ends when the gripper loses contact with the object or when a maximum acceleration is achieved. At this point, a new results file should be generated. Finally, I'll end off with some examples of real-world validation of simulated experiments. First, our simulation predicts the bending of a real block of tofu under different grasps, without needing to fine-tune parameters. Simulation is also accurate in predicting which grasps will induce breakage on the tofu. Breakage should occur at approximately 3 kilopascals. Under grasp A, all stresses are below that threshold. And indeed, no breakage occurs. Under grasp B, there should be breakage that occurs at the gripper edges where stresses are higher. We see that breakage indeed occurs along the edges of the gripper. Under grasp C, breakage should occur along the tofu's long axis. And that's exactly what happens in the real world too. Another example of sim-to-real correspondence is in predicting the drooping of tubes under pickup. Thank you so much for your attention, and we hope that this code-based DefGrasp Sim will be useful for the community going forward.